Thermal fatigue damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of thermal fatigue based on API 571. Thermal fatigue is the result of cyclic stresses caused by variations in temperature. Damage is in the form of cracking that may occur anywhere in a metallic component where relative movement or differential expansion is constrained, particularly under repeated thermal cycling. Thermal fatigue damage refers to the deterioration of materials and components caused by repeated cycles of heating and cooling. This phenomenon typically occurs in environments where materials are subjected to significant thermal fluctuations, leading to the development of thermal stresses. As materials expand when heated and contract when cooled, the repetitive nature of these expansions and contractions can result in the formation of microscopic cracks and other structural weaknesses. Key characteristics of thermal fatigue damage include: Number 1 is crack formation. The dominant feature of thermal fatigue is the growth of cracks, which may initiate at points of high stress or defects in the material. These cracks can expand over time, ultimately leading to structural failure. Number 2 is material properties. Different materials exhibit varying susceptibility to thermal fatigue. Metals, ceramics, and polymers may respond differently to thermal cycling based on their thermal expansion coefficients, yield strengths, and ductility. Number 3 is temperature range. Thermal fatigue is particularly significant in applications where materials experience high temperatures, such as in engines, turbines, heat exchangers, and various industrial processes. Number 4 is thermal cycling. The frequency and magnitude of thermal cycles significantly influence the extent of thermal fatigue damage. Frequent and intense cycling can accelerate damage accumulation. Number 5 is environmental factors. Other factors, including oxidation, corrosion, and mechanical loading, can exacerbate thermal fatigue damage, particularly in harsh operating conditions. Number 6 is loading pattern. Repeated cycles of loading and unloading, rather than a single, monotonic loading, increase the likelihood of thermal fatigue damage. Number 7 is frequency and duration. Higher frequency and longer duration of temperature fluctuations can accelerate material degradation. Number 8 is microstructural characteristics. The presence of defects, such as inclusions, porosity, or microcracks, can initiate thermal fatigue damage. Number 9 is detection and monitoring. Identifying thermal fatigue damage often requires techniques such as non-destructive testing, NDT, methods, including ultrasonic testing, visual inspections, and thermography, to assess the integrity of affected structures. Consequences of thermal fatigue damage. Thermal fatigue damage can lead to a range of consequences, including: Number 1 is reduced material strength. Decreased material strength can compromise the structural integrity of components. Number 2 is fatigue life reduction. Materials with thermal fatigue damage may fail prematurely, leading to catastrophic failures. Number 3 is material embrittlement. Long-term exposure to thermal fluctuations can lead to material embrittlement, making it more prone to brittle failure. Number 4 is corrosion and cracking. Thermal fatigue damage can create an environment conducive to corrosion and cracking. In summary, thermal fatigue damage is a critical consideration in engineering and materials science, particularly for components exposed to cyclic thermal environments. Understanding its mechanisms and implementing strategies for assessment and prevention are essential for ensuring the reliability and longevity of materials and structures in use. Thermal fatigue affected materials based on API 571. All materials of construction. Thermal fatigue is a damage mechanism that occurs in materials subjected to cyclic thermal loads, leading to the development of cracks and eventual failure. The materials most commonly affected by thermal fatigue include: Number 1 is metals. Many metals experience thermal fatigue due to their thermal expansion and contraction during heating and cooling cycles. Common metals affected include: The first is steel, such as in power generation, automotive, and aerospace applications. The second is aluminum and aluminum alloys, used in aerospace and automotive applications. The third is nickel-based superalloys, used in high-temperature environments such as turbines. Number 2 is ceramics. Certain ceramics can be prone to thermal fatigue, especially those used in high-temperature applications, where repeated thermal cycling can lead to cracking and spalling. Number 3 is composites. Composite materials, particularly those with polymer matrices reinforced with fibers, can also be affected by thermal fatigue. The differing thermal expansion coefficients of the matrix and fibers can lead to stresses that initiate cracks. Number 4 is graphite and carbon-based materials. These materials can also show thermal fatigue behavior, especially in applications involving thermal cycling and high temperatures. Number 5 is polymers. While often not thought of in the context of thermal fatigue, some polymers can experience fatigue under temperature fluctuations, particularly thermoplastic materials. In case of thermal fatigue is a damage mechanism that occurs when a material is subjected to repeated thermal cycles, resulting in the material's microstructure to degrade over time. The affected materials of thermal fatigue might be generally divided in two categories. Number 1 is high-temperature materials. The first is nickel-based superalloys. The second is titanium alloys. The third is stainless steels, such as 304 and 316. And the fourth is cobalt alloys, such as Haynes 230 and waspalloy. These materials are susceptible to thermal fatigue due to the following reasons. The first is their high-temperature capabilities make them ideal for applications in engines, turbines, and heat exchangers. The second is they exhibit a significant difference in thermal expansion between the surface and the core during thermal cycles. The third is their high strength and high temperature resistance make them prone to creep and stress rupture under thermal stresses. Number 2 is high-temperature coatings. The first is thermal barrier coatings, or TBCs, based on yttrium-stabilized zirconia, or YSC. The second is rare earth oxide-based thermal barrier coatings, or TBCs. Thermal fatigue is a significant concern in thermal barrier coatings, TBCs, due to the following reasons. The first is they provide thermal insulation and protect the underlying substrate from high temperatures. The second is their high thermal mismatch between the substrate and the thermal barrier coatings, or TBCs, can lead to thermal stresses. The third is their thermal fatigue can cause spallation, loss of material, and lead to a reduction in the lifespan of the component. The thermal fatigue damage mechanism affects these materials by causing cyclic microcracking, crack growth, spallation, and loss of mechanical properties, such as strength, toughness. Understanding the effects of thermal fatigue on these materials is essential to design and develop more durable and long-lasting components for high-temperature applications. The susceptibility of these materials to thermal fatigue largely depends on their ability to withstand thermal stresses, their thermal expansion characteristics, and their microstructural properties. Proper material selection and design considerations are critical in applications where thermal fatigue is a concern. Thermal fatigue critical factors. Thermal fatigue is a damage mechanism that occurs in materials subjected to cyclic thermal loading, leading to the development of cracks and eventual failure. Various critical factors contribute to the thermal fatigue damage mechanism, including: Number 1 is temperature fluctuations. The magnitude and frequency of temperature changes play a crucial role. Higher temperature differentials typically exacerbate thermal fatigue, as materials expand and contract more significantly. Number 2 is material properties. They are the following. The first is thermal expansion coefficient. Differences in the thermal expansion coefficients of materials can lead to stresses at interfaces. The second is yield strength. Materials with low yield strength are more susceptible to deformation and damage under thermal cycling. The third is toughness. Tougher materials can absorb more energy before failure, making them less prone to thermal fatigue. Number 3 is microstructural features. The grain size, phase distribution, and overall microstructure can influence how materials respond to thermal cycles. Certain microstructural characteristics might promote crack initiation and propagation. Number 4 is surface conditions. Surface roughness, coatings, and any existing defects, like scratches or inclusions, can serve as stress concentrators, initiating cracks under thermal cycling. Number 5 is cycle frequency. The rate at which temperature cycles occur can affect how much time is available for the material to relax stresses, with higher frequencies often resulting in more rapid accumulation of damage. Number 6 is mean temperature. The baseline temperature of operation affects the thermal stresses experienced by the material. Prolonged exposure to elevated temperatures can lead to softening and reduce resistance to fatigue. Number 7 is loading conditions. The presence of concurrent mechanical loads, e.g., tensile, compressive, or torsional stresses, can influence thermal fatigue behavior by altering how stresses are distributed within the material. Number 8 is environment. Environmental factors, such as humidity, corrosive media, or oxidizing atmospheres, can interact with thermal cycling and accelerate damage processes through mechanisms like oxidation. Number 9 is cyclic load history. The history of loading, including previous thermal cycles, may impact the current performance of the material, making it either more or less susceptible to additional damage. Number 10 is stress state. The nature of the stress, tensile, compressive, or shear, can influence the initiation and propagation of cracks under thermal cycling. Number 11 is notches and geometrical stress concentrators. Geometric features, such as sharp corners, holes, or notches, can concentrate stresses and promote crack initiation. Number 12 is residual stresses. Manufacturing processes, such as welding, casting, can introduce residual stresses in materials, which can affect crack initiation and growth. Number 13 is service conditions. Real-world operating conditions, such as pressure and the presence of cyclic mechanical loads, can compound the effects of thermal cycling. Understanding these critical factors is essential for predicting thermal fatigue, designing components for thermal cycling conditions, and selecting appropriate materials to mitigate the risk of failure. Thermal fatigue affected units or equipment based on API 571. The first is examples include the mix points of hot and cold streams such as hydrogen mix points in hydroprocessing units, and locations where condensate comes in contact with steam systems, such as desuperheating or attemperating equipment, figures 4:20 and 4:23. The second is thermal fatigue. Cracking has been a major problem in coke drum shells. Thermal fatigue can also occur on coke drum skirts where stresses are promoted by a variation in temperature between the drum and skirt, see figure 4:21 and figure 4:22. The third is tubes in the high-temperature superheater or reheater that penetrate through the cooler water wall. Tubes may crack at the header connection if the tube is not sufficiently flexible. These cracks are most common at the end where the expansion of the header relative to the water wall will be greatest. The fourth is steam-actuated soot blowers may cause thermal fatigue damage if the first steam exiting the soot blower nozzle contains condensate. Rapid cooling of the tube by the liquid water will promote this form of damage. Similarly, water lancing or water cannon use on waterwall tubes may have the same effect. Thermal fatigue is a damage mechanism that occurs in materials and components exposed to cyclic thermal loading, which can lead to cracking and failure over time. This phenomenon is particularly relevant in environments where materials experience significant temperature fluctuations. The affected units or equipment can include: Number 1 is pipelines and pressure vessels. Often found in processing plants, oil refineries, and chemical plants, which may experience rapid temperature changes during operation. Number 2 is heat exchangers and cooling systems. Subject to significant temperature differences between the hot and cold fluids, leading to thermal stresses. for specific locations are in the following. Heat transfer units, such as coils, plates, condensers and evaporators, cooling towers, pumps and valves. Number 3 is boilers. Rapid heating and cooling cycles can create thermal fatigue issues in boiler components. Number 4 is turbine components. In gas or steam turbines, parts such as blades and casings can experience thermal cycling. Number 5 is nuclear reactor and fuel components. Components such as reactor pressure vessels and heat exchangers in power generation can be susceptible to thermal fatigue. For specific locations are in the following. Fuel rods, cladding materials, control rods, and reactor vessel internals. Number 6 is engines. Internal combustion engines, especially the cylinder heads and exhaust systems, experience rapid thermal cycling during operation. For specific locations are in the following. Engine blocks, cylinder heads, engine components such as pistons, connecting rods, and propulsion system components. Number 7 is aircraft and aerospace components. Aircraft engine parts, including turbine blades and exhaust systems, that undergo thermal cycling due to different flight conditions. For specific locations are in the following. Engine components such as compressor blades, turbine blades, heat exchangers such as fuel nozzles, heat shields, and structural components such as airframe, wing skins. Number 8 is industrial furnaces and ovens. The structures or components within these systems can be affected by high temperatures and thermal cycling. For specific locations are in the following. Furnace walls and doors, boiler components such as tubes, headers, and heat transfer surfaces. Number 9 is electrical equipment. Components like transformers and circuit breakers can also suffer from thermal fatigue due to heating and cooling during operation. Thermal fatigue can lead to reduced life expectancy and failure of these components, making it essential to monitor and maintain affected equipment regularly to prevent serious outages or hazards. Appearance or morphology of thermal fatigue damage. Based on API 571. The first is thermal fatigue. Cracks usually initiate on the surface of the component. They are generally wide and often filled with oxides due to elevated temperature exposure. Cracks may occur as single or multiple cracks. The second is thermal fatigue. Cracks propagate transverse to the stress and they are usually dagger-shaped, transgranular, and oxide-filled, see Figure 4, 24 and 4 to 25. However, cracking may be axial or circumferential, or both, at the same location. The third is in steam generating equipment. Cracks usually follow the toe of the fillet weld, as the change in section thickness creates a stress razor. Cracks often start at the end of an attachment lug, and if there is a bending moment as a result of the constraint, they will develop into circumferential cracks into the tube. The fourth is water in soot blowers may lead to a crazing pattern. The predominant cracks will be circumferential and the minor cracks will be axial. See Figure 4, 26 to 4 to 27. Thermal fatigue is a damage mechanism that occurs due to thermal stresses induced by cyclic temperature changes. The appearance or morphology of thermal fatigue damage can vary depending on the material, temperature range, and cyclic loading conditions. Here are some common features associated with thermal fatigue damage. Number 1 is cracking and flaking. The most prominent sign of thermal fatigue is the formation of cracks and flakes on the surface of the material. These cracks can be parallel to the surface, perpendicular to the surface, or at an angle. Thermal fatigue cracks often appear as a network of fine, longitudinal cracks that can be oriented perpendicular to the direction of heat flow or stress. These cracks can be evenly spaced or irregularly distributed. As thermal fatigue progresses, cracks can grow in a transgranular manner, through the grain structure, and intergranular manner, along grain boundaries. Number 2 is surface layer peeling. The surface layer of the material can peel off, exposing a rough, layered surface. This is due to the formation of cracks and delamination of the surface layer. The surface of thermally fatigued components may exhibit fine, hairline cracks, small, rounded or oval-shaped pits and discoloration or oxidation. Number 3 is wear and surface deformation. Thermal fatigue can cause surface wear and deformation, leading to a rough, pitted surface. Cracks typically initiate at stress concentrators such as surface roughness or scratches, material defects, e.g., inclusions, pores, welds or joints, and areas with high thermal gradients. Number 4 is microcracking. Microcracks can form within the material, especially in regions with high thermal stresses. These microcracks can merge to form larger cracks. Number 5 is crazing. In some cases, thermal fatigue can cause the formation of crazes, which are small, network-like cracks that form on the surface of the material. Number 6 is layering or stratification. Thermal fatigue can cause the formation of layers or strata on the surface of the material, as new material is deposited or formed during the cycling process. Number 7 is pitting or corrosion. Thermal fatigue can also lead to pitting or corrosion, especially in materials that are prone to corrosion. Number 8 is ratchet marks. In some cases, thermal fatigue cracks can exhibit ratchet marks or beach marks, which are characteristic markings that indicate the progression of crack growth. Number 9 is material degradation. Repeated thermal cycling can lead to material degradation, such as microstructural changes, such as grain growth, precipitation, and reduction in material properties, such as strength, toughness. Number 10 is geometry-dependent effects. The morphology of thermal fatigue damage can be influenced by the component's geometry, such as curvature or bends, thickness variations, and proximity to edges or corners. In terms of morphology, thermal fatigue damage can be categorized into different types, including: Number 1 is high-temperature oxidation. This type of damage occurs when the material is exposed to high temperatures, leading to the formation of oxide layers. Number 2 is low-temperature embrittlement. This type of damage occurs when the material becomes brittle and cracks form due to thermal stresses at low temperatures. Number 3 is thermal shock. This type of damage occurs when the material is subjected to sudden and extreme temperature changes, leading to the formation of cracks and fractures. These are some of the common features associated with thermal fatigue damage, but the specific morphology can vary depending on the material and loading conditions. Thermal fatigue damage mechanisms: prevention and mitigation. Thermal fatigue damage commonly occurs in materials and structures that experience repeated heating and cooling cycles, leading to the formation and propagation of cracks due to the stresses induced by thermal expansion and contraction. Effective prevention and mitigation strategies include: Number 1 is prevention strategies: material selection. Choose materials that have high thermal fatigue resistance. Materials with lower coefficients of expansion and high thermal shock resistance, such as certain ceramics or advanced alloys, can be beneficial. Number 2 is design considerations. The first of design considerations is geometric optimization. Design parts to minimize thermal gradients. Use uniform wall thicknesses, smooth transitions, and rounded corners to reduce stress concentrations. The first of design considerations is thermal insulation. Implement insulation to maintain uniform temperatures within components and minimize temperature fluctuations that can lead to thermal cycling. Number 3 is controlled heating and cooling. The first of controlled heating and cooling to be considered is use gradual heating and cooling processes instead of rapid changes. Controlled thermal cycling reduces the magnitude of thermal stresses. The second of controlled heating and cooling to be considered is implement slow, staged ramps in temperature changes in manufacturing processes or during operation. Number 4 is surface treatments. Apply coatings and surface treatments that enhance resistance to thermal fatigue. These can improve wear resistance and reduce crack initiation. Number 5 is regular inspections and maintenance. Conduct regular inspections to detect early signs of fatigue damage, such as cracks or deformation. Scheduled maintenance can also ensure that components are operating under optimal conditions. Number 6 is stress relief processes. Post-weld heat treatment or annealing can relieve residual stresses that might contribute to material failure due to thermal fatigue. Number 7 is monitoring and data collection. Utilize temperature sensors and stress monitoring equipment to gather data about thermal conditions and stresses in real time, allowing for predictive maintenance. Implementing monitoring and maintenance strategies such as: the first is regular inspections. Routine checks for early signs of thermal fatigue such as cracks or deformations can help address problems early. The second is condition monitoring. Utilizing sensors to monitor temperature and stress can help manage thermal cycles and predict failures. Number 8 is thermal cycling control. The first is controlled heating and cooling. Implement processes that control the rate of temperature change, thus reducing thermal cycling rates. The second is slow startup and shutdown. Gradual changes in temperature help minimize mechanical stresses associated with rapid thermal changes. Number 9 is use of coatings. Thermal barrier coatings, or TBCs. These can be applied to materials to protect them from extreme temperatures, helping to reduce the thermal gradient and thermal cycling effects. Number 10 is fatigue testing and analysis. Carry out thermal fatigue testing on materials and structures to understand their performance under thermal cycling and incorporate that data into design and operational decision-making. Number 11 is operational practices. Adopt operational practices that limit excessive thermal cycling, such as avoiding unnecessary startups and shutdowns or using temperature-controlled systems. By implementing these strategies, organizations can significantly reduce the risk of thermal fatigue damage, prolonging the lifespan and reliability of affected components and systems. Inspection and monitoring thermal fatigue damage mechanisms based on API 571. Since cracking is usually surface-connected, visual examination, MT and PT are effective methods of inspection. And then, external SWUT inspection can be used for non-intrusive inspection for internal cracking and where reinforcing pads prevent nozzle examination. And then, heavy wall reactor internal attachment welds can be inspected using specialized ultrasonic techniques. Thermal fatigue occurs when materials experience repeated thermal cycles, leading to cracking and other forms of damage. Detecting such damage is crucial, especially in industries like aerospace, power generation, and automotive. Various inspection and monitoring methods can be employed to detect thermal fatigue damage. Number 1 is visual inspection. Surface cracks inspection for visible surface cracks or discoloration can provide initial indications of thermal fatigue. Number 2 is non-destructive testing, or NDT. Techniques such as dye-penetrant inspection can help highlight surface-breaking cracks. There are several methods of non-destructive testing, or NDT. The first method is ultrasonic testing, or UT. This method uses high-frequency sound waves to detect internal flaws. It is particularly useful for identifying subsurface cracks that may develop due to thermal fatigue. The second method is radiographic testing, RT. X-ray or gamma-ray imaging can reveal structural issues and internal cracks that are not visible on the surface. The third method is eddy current testing. Eddy currents can detect surface and near-surface cracks in conductive materials. This method is effective in identifying changes in material properties due to thermal fatigue. The fourth method is magnetic particle testing, or MT. For ferromagnetic materials, this method can detect surface and near-surface cracks by applying magnetic particles to the surface and observing how they cluster around defects. Number 3 is acoustic emission monitoring. This involves listening for high-frequency sound waves emitted by crack growth when the material is under stress or thermal cycling, allowing for real-time monitoring of damage progression. Number 4 is thermography. Infrared thermography can identify temperature variations on a component's surface that may suggest underlying flaws, such as delamination or cracking resulting from thermal fatigue. Number 5 is fiber optic sensors. These sensors can be embedded in a material to monitor strain and temperature changes, providing real-time data on structural health and potential thermal fatigue development. Number 6 is digital image correlation, or DIC. A non-contact optical method used to measure deformation and strain on a material's surface can help in understanding how thermal cycles affect structural integrity. Number 7 is fractography. Examining fracture surfaces using scanning electron microscopy, or SEM, can reveal the microstructural features associated with thermal fatigue and help in understanding the failure mechanisms. Number 8 is mechanical testing. Destructive testing methods, such as fatigue tests on similar materials or components, can yield information about the material's behavior under thermal cycling. Number 9 is finite element analysis, or FEA. While not an inspection method, finite element analysis, or FEA, can be used to model thermal fatigue behavior and predict failure points in components based on operational conditions. In conclusion, selecting the appropriate inspection and monitoring methods for thermal fatigue damage detection often depends on the specific application, material type, and component geometry. Combining several techniques may enhance the probability of detection and provide a more comprehensive assessment of the component's condition. Thank you.